Okay, my apologies. I don't know what happened. I just got lost. So we were saying that this is the radius. This is the radius. This is the azimuth angle, and from bottom from the base going up, that is the z. And these are the three dimensions of the cylindrical coordinate system. Now, of course, we can see that we have described those points, and now we can see that each of the three dimensions varies from between varies between being 0 to infinity. The phi is of course varying between 0 to 2 pi, and z is varying from negative theta to positive theta. And what you can observe is that I can see someone is trying to chat. Let me confirm. I hope it's a serious message for everyone. No, he's saying that I'm not audible, but I guess others can hear me. We can confirm from your side. I think Daniel, you can unmute you can refresh or join back in because others can hear. Can others confirm that you can hear me just via chat? Yeah, it's okay. So, Pilote, thank you. You're always helping us resolve those small issues that might arise. So, thank you very much. So, we are saying that it is important to know the limits of each of these, that radius can never be negative, but it will always be between 0 to infinity. Again, the phi can never be negative, it is always 0 to 2 pi. But we are saying that z can be negative from negative infinity to positive infinity. The reason is because from the cylinder that we have, oh yeah, I think I never shared this full screen. Let me share. Okay, new share the screen one. Share. Okay. I believe you can see my new screen I have shared. So I am now referring to this cylinder, and you're saying that sometimes we may consider the origin to be somewhere at that point. And therefore, I can go downwards from point 0. This is point 0 of z, and I can go downward to have negative 2z. Z is equal to negative 2. Okay, so that is possible, and that is important that you realize that our z can take a negative value. So now we want to describe a vector in a cylindrical coordinate system, and we are saying that we describe vectors for the Cartesian using ax, ay, and az. So now we are saying that it is similarly possible to describe a vector in a Cartesian in a cylindrical coordinate using a rho, a phi, and az. And I remind you people that you needed to log in using your full names and registration number, because I will submit this list to the university. And therefore, when you log in with some fancy names like Infinix Smart 2, you are not helping us, or you're not helping yourself. So I plead with you to log in using at least you can of course rename yourself with the appropriate name. So this is where we are, that we are saying that we can describe a vector in a cylindrical coordinate system using three different dimensions, that is a rho, a phi, and az. Now, and of course, you can see that we have now new unit vectors, a rho, a phi, and az. So you can remember how we defined the unit vectors. So we are saying now we are introducing them, and now we are saying that if of course these are the unit vectors in the directions of rho, phi, and z respectively. We have seen that diagram. Now note that A5 is not in degrees. A5 is in the, it has the units of the vector that it describes. And we are giving an example here that if a force acts on a particle in a circular motion, so assume that this is my coordinate system, and I have a force that is acting on a particle here in a circular motion. So such that you can even consider a very simple example that you are at the center here and you have a rope, and a rope is holding a ball, and you are rotating that ball loud yourself. So we can say that that ball is experiencing a force F that can be described by the angle that the angular velocity that the angle is moving with, and of course it's the radius from where the origin to where the ball is can also be described by rho, and etc., etc. So I think that example is important, that you should not always confuse that A5 will always have the dimensions of degrees. So as we said with the Cartesian coordinates, the magnitude of a vector, remember this is a vector and this is how you express the magnitude. We normally say A vector, if you are writing it, arrow at the top, and then 2 bars on each side. That describes the magnitude. I'm repeating that for the sake of those who might have missed our first and second lectures. Now, having said that, that is how you describe the magnitude by saying that each of the scalar components in either of the directions of the cylindrical coordinate system is squared, and then you find the square root. That gives you the magnitude. Note that the unit vectors A5, A rho, and AZ are mutually perpendicular. That's something we have already said. And therefore, the axioms, remember the last class we mentioned the concept of axiom. The axioms of electromagnetics or vectors, we can define them. We say that when you dot the same unit vector, you get a 1. We're saying that A rho dot A rho is equal to 0. Sorry, A4 dot A rho. Oh my goodness, what is happening to myself? A rho dot A rho is equals to 1. A5 dot A5 is equals to 1. And AZ dot AZ is equals to 1. That is what we said about the dot product. Someone is raising his hand. I can see Isaac. I'm unmuting you, so you can speak. Tell us what's up. You can even unmute yourself.
I don't think my hand is raised.
Of course, your hand is raised. Everybody can see. Okay, fine. You continue. We continue then. You mute yourself. Yeah, we continue then. Vicky Chebi is saying he can't hear. Just join back. You can log out and log back in. These are sometimes the challenges of technology. Others can hear me. Therefore, someone advised Chebi to log out and log back in. That is for, I don't want to write that because some people might confuse that. So someone advised Chebi to log back in. I don't know how that happens because she has now written privately. I don't have time to respond to her. Probably I might do that. Oh. I'll log back in if you have a problem. Okay, so I think that's fine. So then remember what we said about the cross product of unit vectors. We said that A rho we say that when you cross a product, two unit vectors, we were following what we described as cyclic permutation. Like we arrange these unit vectors in a circle. So we say this first point is AX when referring to the cylindrical coordinates. The next one is AY in that order. And the third one is AZ. And you say that you follow cyclic permutation by saying that AX cross AY is equals to AZ. Then you can start somewhere else. You can also say that AY cross AZ is equals to AX. So this is equal sign, this is cross sign. So we are doing the same thing with with cylindrical, and we are saying that we arrange them in the order of. I think I can just jump to. I can just come here and say that I arrange A law. Then after A row, you go to A5, just the way we arrange them, and then we go to AZ, and then you can say that is, and the arrow is going back. So you can say that A row cross A5 is equals to AZ. You can also start the other way around. I think the best one was to draw an A row at that point. Then you say A5 at that point. You say AZ at that point. Then you are saying that you are going in the clockwise. So you see that is AX cross A row cross A5 that gives you AZ equal sign. Then you can start somewhere here. You can start AZ cross A row will give you what? Will give you A row. So you can always work with that diagram. With that cyclic permutations, they always give you how we do those cross product. So I move back to my diagram here, and I'm saying that is what we have done with this cross product right there, and therefore we should not confuse anyone about how we are getting to those axioms of vectors. All right. So something also we should also now understand is that sometimes we might move from Cartesian and you move to Cartesian, and you might require to move some of them to cylindrical, or you might move from cylindrical back to Cartesian. And that might be required. You might be when you're describing a point. Also, you might be describing a vector from cylindrical to Cartesian and Cartesian to cylindrical. Similarly, when we have done that, we might also move from cylindrical to spherical. We might, after you have moved, we might also move back to cylindrical, and we might still move from cylindrical to Cartesian, and we might move from Cartesian to spherical. So I think these are the ideas you're going to be working with. And just that is the idea. So having said that, so what we are saying is that from this diagram that I have shown right here, I think I'm still sharing the screen. From this diagram, which I can now redraw it down here. So I'm saying that you at some point you might want to express this point using or you might, let's say you might express the radius rho using the XYZ coordinate system. And that would mean, how would you get the radius, this radius here, which is the same as the one that was up here, this row, using the X and Y. And it is something quite simple, because we are saying that the row becomes like a diagonal, which is described by this. So I'm saying that we said that X and Y make a right angle. And therefore, if this is my X and this is my Y, the Y which is parallel to this one, then you can say that this hypotenuse can be described by what? You can say that sine of phi is equals to y over rho. And therefore, you can express a rho or rho to be equals to y over sine phi. Or alternatively, you might say y can be expressed in terms of rho as y is equals to rho sine phi. Similarly, you might say that cosine of phi is equals to x over rho. And therefore, you might still express your rho in terms of, I'll bring this one here and say that is equals to x all over cosine of phi. So these ideas are pretty straightforward. You can say that x from this equation can be expressed as rho cosine of phi. So these are the ideas that we are working with, and we are therefore saying that, having said that rho is now a hypotenuse, it is very easy to say that it can be expressed as the square root of x squared plus y squared, and that again is coming from pure mathematics that we have dealt with in the past, because as you can see that this never described uh, the entire value of x, because at that point we were cutting x at that point. So I'm saying x prime. So if we wanted to find the hypotenuse rho, which is now coming from both x, the full x is coming from there to there, and the full y, which is coming from there to there. All you need to do is see that it's coming from a rectangle that has length. This is my x, and my y is going like that, and therefore this is my right angle triangle. This is my hypotenuse rho, and therefore obviously we know that rho is given by root of x squared plus y squared. So again, I don't have to teach you the basics of mathematics because you have gone through them before. That is something you can get, and we can also see that we can be able to get phi from the coordinate system, from the Cartesian coordinate system, by simply saying that from this diagram that we have here, if I was to repaste it there, I would say that if again you wanted to find what is theta, what is phi in terms of x and y, you can simply say that it is tan inverse. We normally say that tan, or we normally say tan of phi is equals to opposite. And if this is my phi, my opposite must be y. So this must be y over x. Therefore, if you wanted to find phi, you'd say is equals to tan inverse of y over x. And again, that is from your trigonometry. So that is the one I have just shown you right there. And of course, as you can see, cylindrical z is the same as Cartesian z. Therefore, z will become z. So here you are trying to transform a point that is described by radius in Cartesian, in cylindrical by its Cartesian coordinate system. And again, it was described by angle phi, and we are trying to describe that using its Cartesian coordinates. And again, z doesn't change, as we have seen. remains the same. So I think that describes it. And of course, you can do the reverse. These are the things I was showing you earlier. You can express X, Y, and Z from now X, from the cylindrical to the Cartesian, and pretty much works like that. So these are ideas that I believe you will get used to them pretty soon. You should not join with video. When you have joined, just join without video and you'll be good to go. Don't really expose us to using force not to see you. Now. I think, of course, you should always take a break and I give people some chance to fight. If there's any question, you can write it on chat. I will respond. Meanwhile, I take a glass of water. So now we want now to find the relationships between Cartesian and cylindrical in terms of vectors. The vectors being the unit vectors for each coordinate system. And here is the idea that you might, the transformation from AX to arrow is not like straightforward. It's not like, okay, it is straightforward, but it is not something that you do on the fly. You have to understand how each of these is expressed. And I will refer to diagram that to figure 2.3 that is described in here below. I had tried to do some demonstrations earlier, therefore, so that I would spend less time. And here is the idea that first of all, you want to convert X, okay, from cylindrical components to Cartesian unit vectors. And so here we have X and Y, of course, X and Y, which is in Cartesian. And we are saying that if we converted this one to become my cylinder would be centered at this point, and therefore this would become my base of the cylinder. And therefore we are saying that the radius rho, which is now going to be described by the unit vector a rho, can be expressed as follows. That consider that this is my angle theta. Consider that this is my angle theta, my angle phi, and therefore the unit vector that is described by the radius is going to be described by arrow. So of course the arrow is going to be the radial direction or moving outward from the center of the cylinder. And the angle phi, which is going to be described by unit vector a phi, is tangential to the point of, it's a tangential to the surface of the cylinder. And therefore, since it is moving from X to Y, the direction, if this was my point of contact, just look at this point, if this is my point of contact, then, and you want to look at the tangent, it would be a straight line in that direction. And this would be my unit vector a phi cap. That is the direction. And therefore, if we were to consider it in the reverse direction, it would be negative a phi. And we have said that